This lesson is for grade 11 General Mathematics. Quarter 1, Module 5. The topic is Exponential Functions. This lesson is outlined in this manner. 1. Definition of exponential expression. 2. Description and examples of exponential function, exponential equation, and exponential inequalities. 3. Exponential functions and their transformations. 4. Exponential growth and decay. 5. Compound interest. And 6. The natural exponential function. After this lesson, you are expected to first define exponential function, exponential equation, and exponential inequalities. Second, distinguish among exponential function, exponential equation, and exponential inequalities. Third, know the concept of exponential functions. Fourth, differentiate exponential growth and decay. And fifth, represent real-life situations using exponential functions. Let us start in Lesson 1, representing real-life situations using exponential functions. Please open your Module 5 on page 8. Exponential functions occur in various real-world situations. Exponential functions are used to model real-life situations such as population growth, radioactive decay, carbon dating, growth of an epidemic, loan interest rates, and investments. Some things can be counted by multiplying continually. Recall the concept of geometric sequence or progression studied in grade 10, in which each term after the first is obtained by multiplying the preceding term by a non-zero constant called the common ratio. Symbolically, if A is the first term and R is the common ratio, then the first term is A, the second term is A times R, the third term is A times R raised to 2, and the fourth term is A times R raised to 3, and so on and so forth. So forms a geometric sequence. For example, bacteria reproduce by splitting, doubling the number of bacterial cells. If there are 7 cells and a doctor is examining the bacteria, after a certain time, there will be 14 cells, then 28, then 56, and etc. The terms 7, 14, 28, 56, and so on can be written in factored form or exponential form as shown in the table below. What's in? The table below has 3 columns. The first column is represented by term, second in factored form, and the third in exponential form. Under the term, we have a sub 1 is equal to 7, a sub 2 is equal to 14, a sub 3 equals 28, a sub 4 equals 56. The next column in factored form, we have 7, next is 7 times 2, and next is we have 7 times 2 times 2, and the next is 7 times 2 times 2 times 2. So in exponential form, the first is 7 times 2 raised to 0. Second is 7 times 2 raised to 1. Third, we have 7 times 2 raised to 2. And fourth, 7 times 2 raised to 3. This means that if there are 7 bacteria initially and doubles after a certain time, then there will be 7 times 2 raised to n minus 1 after n units of time. In general, given the first term a sub 1 and the common ratio is r of a geometric sequence, then the nth term of the sequence is a sub n equals a sub 1 times r raised to n minus 1. So that is our formula. What is it? Let's start with the definition. An exponential expression is an expression of the form a times b raised to x minus c plus d, where b is greater than 0 and b is not equal to 1. Take note of the condition b is greater than 0 but must not equal to 1. Why? Because if a constant 1 raised to any positive exponent, that will always be equal to 1, and that will become a constant function, not an exponential function. The definitions of exponential equations, inequalities, and functions are shown below. So the definition of exponential equation: an equation involving exponential expressions. Example, 7 raised to 2x minus x squared equals 1 over 343. So in an exponential equation, since we're talking about equation, there is an equal sign. For exponential inequality, the definition is an inequality involving exponential expressions. Example, we have 5 raised to 2x minus 5 raised to x plus 1 less than or equal to 0. So since we are using an inequality sign which is less than and equal to, so this means this is an exponential inequality. For the exponential functions, definition: function of the form f of x equals b raised to x, where b is greater than 0 and b is not equal to 1. Example, f of x equals 1.8 raised to x, or y is equal to 1.8 raised to x. Take note our b here, which is 1.8, that is greater than 0 but not equal to 1. So this is an exponential function. An exponential equation or inequality can be solved for all x values that satisfy the equation or inequality. An exponential function expresses a relationship between two variables such as x and y, and can be represented by a table of values or a graph. Now let's have solve examples. That is on page 10 of your module. Determine whether the given is an exponential function, an exponential equation, an exponential inequality, or none of these. So for number 1, we have f of x is equal to 5x squared. So the answer is none of this. So that is not part of the exponential equation, exponential inequality, and exponential function. For number 2, we have 2 is greater than or equal to 1/2 raised to x. So the answer is exponential inequality. Number 3, 7 raised to 4x is equal to y. It is an exponential function. Number 4, 4 times 100 raised to x minus 2 equals 500. This is also an exponential equation. Number 5, 7 is less than 49 raised to x plus 3. This is an exponential inequality because of the inequality sign that is less than. Number 6, y is equal to 0.5 raised to x. This is an exponential function. Let's have another definition. An exponential function with the base b is a function of the form f of x is equal to b raised to x, or y is equal to b raised to x, where b is greater than 0 and b is not equal to 1 or should not be equal to 1. The base b is restricted to positive real numbers to ensure that f of x is always a real number. So the base b is restricted to positive Take note, positive real numbers but should not be equal to 1. Also, b cannot be equal to 1, for if b is equal to 1, then f of x is equal to 1 and it will be a constant function. Before we proceed to our first example, let us recall first that negative exponents indicates that we need to move the base to the other side of the fraction line. For example, number 1, if you have 3 raised to negative 2, that is equivalent to 1 over 3 raised to positive 2. And that is equal to 1 over 9. Another example, 1/3 raised to negative 2, that is equivalent to 3 over 1 raised to positive 2, equals 3 raised to 2, and that is equal to 9. The definition for negative exponents. We define a negative power as the multiplicative inverse of the base raised to the positive opposite of the power. Example, you have 3 raised to negative 5, that is equivalent to 1 over 3 raised to positive 5. That is, the 1 over 3 raised to positive 5 is the multiplicative inverse of 3 raised to negative 5. So now we have a positive exponent that is equal to 1 over 3 raised to 5 equals 1 over 243. So we are going to use this concept in solving the next example. Example number 1. Complete a table of values for x is equal to negative 3, negative 2, negative 1, 0, positive 1, positive 2, and positive 3. For the exponential functions, the first exponential function is y is equal to 1/3 raised to x. Second exponential function is y is equal to 10 raised to x. And the third exponential function is y is equal to 0.8 raised to x. For our solution, let us start first with y is equal to 1 over 3 raised to x. The first value of x is negative 3. So that becomes y is equal to 1 over 3 raised to negative 3. So that is equal to 27. And then, the second value of x is negative 2. Y is equivalent to 1 over 3 raised to negative 2. That becomes 3 raised to 2. That is positive 9. Next value is negative 1. Substitute negative 1 to the value of x. Y is equal to 1 over 3 raised to negative 1. That will equal to 3. Now if x is 0, so any number raised to 0 is 1. The answer is 1. Now if x is positive 1, so that is y is equal to 1/3 raised to positive 1, that is equal to 1/3. Now if x is equal to positive 2, y is equal to 1/3 raised to positive 2, that is equivalent to 1 over 9. And if x is positive 3, so you have y equals 1 over 3 raised to 3, that is equivalent to 1 over 27. Number 2 solution, our exponential function is y equals 10 raised to x. If x is negative 3, that becomes 10 raised to negative 3 is equal to 1 over 1000. If x is negative 2, we have another negative exponent that becomes y equals 10 raised to negative 2. So we have 1 over 10 raised to positive 2. That becomes 1 over 10 that is raised to 2. And that is equal to 1 over 10 raised to 2 is positive 100. For x is negative 1, we substitute negative 1 to the value of our x. Y is equal to 10 raised to negative 1. That becomes 1 over 10. For x is equal to 0, y is equal to 10 raised to 0. So any number raised to 0 is positive 1. So the answer is positive 1 here. If x is equal to positive 1, So let's substitute positive 1 in our exponential function. We have 10 raised to positive 1, that is equal to positive 10. Now for x is positive 2, so 10 raised to positive 2, that is equivalent to 100 because it is 10 times 10. Now if x is positive 3, so you have 10 raised to positive 3, that is 10 times 10 times 10. So that's why we get 1000. That's for solution number 2 for our number 2 exponential function. Now let's proceed to solution number 3, our exponential function y equals 0.8 raised to x. So we are going to substitute the x, which is our exponent, with the given values of x. The first value is negative 3. So 0.8 raised to negative 3, that is equivalent to 1.953125. Since our exponent is negative 3, all we have to do is to get the reciprocal of this one, that is 1 over 0.8. 1 over 0.8 raised to positive 3, so we get 1.9531. Now for x is negative 2, so 0.8 raised to negative 2, that is equal to 1 over 0.8 raised to positive 2. That is equivalent to 1.5625. Now for x is negative 1, so we have 0.8 raised to negative 1, that is equal to 1 over 0.8 raised to negative 1, that is equivalent to 1.25. Now if our x is 0, so any number raised to 0, that is automatically equal to positive 1. If x is positive 1, so 0.8 raised to positive 1, we get 0.8. Now if x is positive 2, so you have 0.8 raised to positive 2, so we have 0.64. For x is positive 3, so 0.8 raised to positive 3, so we get 0.512. Example number 2. If f of x is equal to 3 raised to x, let's evaluate the f of 2, f of negative 2, f of 1/2, f of 0.4, and f of pi. Solution. For f of 2, all we have to do is to change x into positive 2. So we have f of 2 is equal to 3 raised to 2 equals 9. For the f of negative 2, so all we have to do is to change x with negative 2. That is 3 raised to negative 2. And that is equal to, so since it is a negative exponent, all we have to do is to get the reciprocal, that is equal to 1 over positive 3 raised to 2. And that is equal to 1 over 9. For f of 1/2, take note, our x value here is 1/2. So our function or exponential functions will become 3 raised to 1/2. Next is f of 0.4. We are going to substitute 0.4 in x. So that it becomes 3 raised to 0.4, and that is equal to the 0.4 is equivalent to 2 over 5. That is 4 over 10 or 2 over 5. And 3 raised to 2 over 5 is equivalent to the 5th root of 3 raised to 2. And that is equal to 5th root of 9, because 3 raised to 2 is equal to positive 9. Now the last is the f of pi. Okay, since pi is equivalent to 3.14159 is irrational, the rules for rational exponents are not applicable. So we define 3 raised to pi using rational numbers. So f of pi is equal to 3 raised to pi can be approximated by 3 raised to 3.14. We define 3 raised to pi using rational numbers. F of pi is equal to 3 raised to pi. Can be approximated by 3 raised to 3.14159. Intuitively, one can obtain any level of accuracy for 3 raised to pi by considering sufficiently more decimal places of pi. Mathematically, it can be proved that these approximations approach a unique value which we define to be 3 raised to pi. We have here another definition. Let b be a positive number not equal to 1. A transformation of an exponential function with base b is a function of the form f of x equals a times b raised to x minus c plus d, where a, c, and d are real numbers. Take note, the a, c, and d are real numbers. There are many real-life situations that can be represented using exponential functions and their transformations. Some of them are population growth, exponential decay, and compound interest. Let's start first with the population growth. On several instances, scientists will start with a certain number of bacteria or animals and watch how the population grows. For example, if the population doubles every 3 days, then this can be represented as an exponential function. Example number 3. Let t is equal to time in hours and t is equal to 0. There were initially 20 bacteria. Suppose that the bacteria double every 100 hours. Give an exponential model for the bacteria as a function of t. Now, let's have the solution. Initially, at t is equal to 0, the number of bacteria is equal to 20. At t is equal to 100, the number of bacteria is equal to 20 times 2, because the bacteria double every 100 hours. Next is at 200. At 200, the number of bacteria is equal to 20 times 2 raised to 2. An exponential model for these situations is y is equal to 20 times 2 raised to t over 100. Exponential model for population growth. Suppose a quantity y doubles every t units of time. If y sub 0 is the initial amount, then the quantity y after t units of time is given by y is equal to y sub 0 times 2 raised to small letter t all over the capital T. Radioactive decay. The disintegration of substances is another situation that shows exponential change. Each hour, a fraction of the atoms of a radioactive substance randomly changes into different atoms. For example, they decay. Definition: the half-life of a substance is the time it takes for half of the substance to decay. Now let's take an example number 4 for radioactive decay. Suppose that the half-life of a certain radioactive substance is 10 days and there are 10 grams initially. So letter A, determine the amount of substance remaining after 30 days. And letter B, give an exponential model for the amount of remaining substance. Solution: we use the fact that the mass is half every 10 days from the definition of half-life. Let t equals time in days, thus we have initially at time 0 or t is equal to 0, the amount of substance is 10 grams. At t is equal to 10, the amount of substance is equal to 10 times 1/2, that is equivalent to 5 grams. At T20, the amount of substance is equal to 10 times 1/2 raised to 2. So that is equal to 2.5 grams. At T30, the time is 30. Amount of substance is equal to 10 times 1/2 raised to 3. That is equal to 1.25 grams. The amount of substance remaining after 30 days is 1.25 grams. Letter B. An exponential model for this situation is y is equal to 10 times 1/2 raised to t over 10. We have here an exponential model for radioactive decay. If the half-life of a substance is t units and y sub 0 is the amount of the substance corresponding to t is equal to 0, then the amount y of substance remaining after t units of time is given by y is equal to y sub 0 times 1/2 raised to small letter t over capital letter T. Now let's have the compound interest. A starting amount of money, called the principal, can be invested in a certain interest rate that is earned at the end of a given period of time, such as 1 year. If the interest rate is compounded, the interest earned at the end of the period is added to the principal, and this new amount will earn interest in the next period. The same process is repeated for each succeeding period. Interest previously earned will also earn interest in the next period. Let us take the example number 5. Mrs. De La Cruz invested 100,000 pesos in a company that offers 6% interest compounded annually. Define exponential model for this situation. How much will this investment be worth at the end of each year for the next 5 years? Solution. Let t be the time in years. Then we have, initially at t is equal to 0, amount of investment is 100,000. At t is equal to 1 for the first year, the amount of investment will become 100,000 plus the 6% of 100,000, that is equal to 106,000 pesos. At t is equal to 2, the amount of investment is equal to 100,000 times 1 plus 0.06, that is in the second year, equal to 100,000 times 1 plus 0.06 plus another 6% of 100,000 times 1 plus 0.06, and that is equivalent to 112,360. At t is equal to 3, that is in year 3, amount of investment is equivalent to 100,000 times 1 plus 0.06 raised to 2, or quantity 1 plus 0.06 raised to 2 times 100,000. That is equivalent to 100,000 times quantity 1 plus 0.06 raised to 2 and another 6% of 100,000 times 1 plus 0.06 raised to 2, and that is equivalent to 119,101.60. Following the pattern, we can simply solve a certain amount of investment at t period of time. At t is equal to 4, amount of investment is equivalent to 100,000 times the quantity 1 plus 0.06 raised to 4. That is equivalent to 126,247.70. At t is equivalent to 5, amount of investment is equivalent to 100,000 multiplied by quantity 1 plus 0.06 raised to 5. That is equal to 133,822.56. An exponential model for this situation is a equals 100,000 times quantity 1 plus 0.06 raised to t. Or simply, A is equivalent to 100,000 times 1.06 raised to t. That's it for our compounded interest. Exponential model for compounded interest: if a principal, that is capital P, is invested at an annual rate of small letter r, compounded annually, then the amount after t years is given by A is equivalent to P times quantity 1 plus r raised to t. For number 6 example, referring to example number 5, is it possible for Mrs. Dela Cruz to double her money in 8 years? How about in 10 years? So let's have this solution. Using the exponential model, A is equal to 100,000 times 1.06 raised to t. We substitute t is equivalent to 8. If t is equal to 8, A is equal to 100,000 times 1.06 raised to positive 8. That is more or less equivalent to 159,384.81. That is for 8 years. Now let's solve for t is equal to 10 for 10 years. So A is equivalent to 100,000 times 1.06 raised to 10. More or less, that is equivalent to 179,084.77. Since Mrs. Dela Cruz money still has not reached 200,000 after 10 years, then she has not doubled her money during this time. Now, let's have the natural exponential function. Some situations can be modeled using the exponential function with base e, an irrational number, whose value is approximately 2.71828. At this point, we will just rely on the scientific calculator to obtain further decimal expansion of e. Now we have the definition. The natural exponential function is a function defined by f of x is equal to e raised to x, where our e is our irrational number and our x is our exponent, for all x real numbers. Now let's take example number 7 for this natural exponential function. A radioactive substance is decaying according to the function y is equal to 500 e raised to negative 0.02 times t, where y milligram is the amount present in t years from now. How much will be left after 10 years? Our solution, so we are going to substitute t equals 10 to the given function. Using a scientific calculator, we have y is equivalent to 500 e raised to negative 0.2, that is more or less equal to 409. So that is how are we going to solve for the natural exponential function. What's more, please have your pen and your paper and let's do the activity 1, exponential function defined. You have to determine whether the given is an exponential function, an exponential equation, an exponential inequality, or none of these. Let's start with number 1. 49 raised to x is equal to 7 raised to 2. Number 2. 3 less than 9 raised to x. For number 3, y equals 81 raised to x. Number 4, 3 times 15x equals 45. Number 5, 3 is greater than or equal to 9 raised to x minus 1. Number 6, y equals 1.25 raised to x. Now let's proceed to next activity. Activity 2, evaluation of exponential function. Given the exponential functions, complete the table of values for x is equal to -2, -1, 0, +1, and +2. Our first exponential function, y equals 0.1 raised to x. Again, number 1 exponential function, y equals 0.1 raised to x. Number 2 exponential function, we have y equals 3 raised to x. Again, for number 2 exponential function, y equals 3 raised to x. Number 3, we have y equals 2/5 raised to x, or 2/5 raised to x. Again, number 3, y equals 2/5 raised to x, or 2/5 raised to x. Then, let's have activity 3, exponential models. Give exponential model for the following situations. Situation number 1. At time t is equal to 0, 500 bacteria are in Petri dish. This amount triples every 15 days. So you are going to give an exponential model for that situation. Again, for number 1 situation, at time t equals 0, 500 bacteria are in Petri dish. And this amount triples every 15 days. Number 2 situation, the half-life of a substance is 400 years. Initially, there are 100 grams of substance. Again, for number 2, the half-life of a substance is 400 years. Initially, there are 100 grams of substance. Number 3, suppose that a couple invested 50,000 in an account when their child was born to prepare for the child's college education. That's it. Now you have 3 activities for this lesson.